Okay, so that's our goal. Now, believe it or not, a part of this has to do with where a lot of this comes from. At least some of the pictures I'm going to show you. So like the Mandelbrot set. The Mandelbrot set, you may have seen it before. It kind of looks like I don't know what it looks like. It just looks like sort of Baroque art or something. I'll show you a picture here in a little bit. The Mandelbrot set is the most complex structure probably in the universe because it has infinite complexity. And the way we build something like that is just this very simple algorithm that's built on the complex plane. And this is where we left off yesterday. I'm almost done with this. The math part is about done. So the complex plane, remember what we said, and I want you to make sure you appreciate what this is. The complex plane, the first part is the real axis. Now, that is the stuff you talked about in grade school. That's just the number line, right? Make sure you get that straight. All the numbers you've ever talked about fit on the real axis. The imaginary axis is what we're adding to build the complex plane. But if I look at this complex plane, this number line right down here, this is the same one you've always used. There's 0, there's 2, there's 4. Any number you could, doesn't matter if it's a square root or if it's pi or if it's a decimal or a fraction, they're all contained on that line. What we did yesterday is we took that line of all the numbers we've ever considered and we expanded it. We expanded it to be not just a line, but a plane. And this plane allows us to include these imaginary parts of these numbers. And so if we look at the number -2 plus 5i, instead of just being a number on this line now, it's left the line and it's somewhere else in this complex plane. If I want to think about a number like I'm used to talking about, like for example, if I want to talk about the number, let's take the number -3. What that really is -3 plus 0i. But we just never knew about the plus 0i part. The plus 0i part means that the coordinates of this thing are just -3, 0. All we ever knew about was just the -3 part. But the 0 part is actually there. Okay, it's just on the real axis. Now, that's different from this number right here. -2 plus 5i, sure, that has a real part that's -2. So the real part is just back 2, but it's also got this imaginary part that we're adding to it, the 5i, which moves it off the plane, moves it vertically, or off of the line, vertically, up into the plane. Okay? And then what we ended up saying, so we can plot these points, that's no big deal. What we ended up saying about this that was kind of important at the end, and I don't feel like I had a chance to really explain this well enough, was that the distance that all these points are, if we plot these numbers in the complex plane, the distance they are from the origin is important, because that has to do with their values. Now, in the past, we've said things like, how far is the number -3 from 0 on the real axis, the real number line? 3. And how do we get that? Absolute value, right? That's what absolute value means, the distance from 0 on a number line. The absolute value of -3 is just 3. Count it. 1, 2, 3. Easy. If we want to expand that, though, and ask the question, how far is, say, this point up here, this point from the origin, well, now it's a little bit more complicated because it's not just on that line anymore. It's on the plane, right? And so when we say something like the absolute value of -2 plus 5i, we got to deal with that differently. And the way we do is just the distance formula. Right? It's just equal to the square root of -2 squared plus 5 squared. That's it. Okay? In general, we could just take any point we want to on this plane. Like say we take the point right here, and it's going to be the number a plus bi. I'm not even going to specify what a and b are. They could be anything. But if the coordinates of this point right there are ab, then its distance from the origin just follows the simple formula. The distance formula just ends up becoming the square root of a squared plus b squared. So that tells us how far it is from the origin. Okay? And it's important to know that. When we deal with complex numbers, we got to know how big are they, how far are they from the origin, and that's what the absolute value tells us. Okay, and so we end up with this formula. There it is, square root of a squared plus b squared. That's what absolute value means to us now. If b is 0, if it's on the line, the square root of a squared is just the absolute value of a. So what would, take just a couple quick examples. How far is that number from the origin? What's its absolute value? What's a? -2, because remember the complex numbers, standard form for a complex number is just a plus bi. A is just going to be the real part, and bi is the imaginary part, right? So a is -2. What's b? 5. So then the answer is just going to be the square root of a squared plus b squared. The square root of -2 squared plus 5 squared. And really, if we square a negative, what do we always do? Square the positive. So we just get square root of 4 plus 25 square root of 29 is our answer. That's how far, that's the value, the absolute value of that number, how far it is from the origin. What about this one? That looks a little strange. What's a? 0. Yeah, it's 0. It doesn't show up there, so it must be 0, right? This is the same thing as saying -6i is really just 0 minus 6i. Right? Everybody see that? And so if I want to find how far it is from the origin, I just have the square root of 0 squared plus -6 squared. Well, what's that? 36. Square root of 36 is 6. Okay? We could have taken a shortcut there. Because this number right here, because it doesn't have, now we're used to the real numbers having no imaginary part, but the pure imaginary numbers have no real part. The pure imaginary numbers that don't have an a, or where a is 0, they line up on the vertical axis in the complex plane. And they're just as easy to find their distances from 0. I just know that the distance would be the absolute value of 6, which is, or -6, which is 6. If I were to graph it, it's easier to see. Look, if I graph this guy, whoops, hang on, I gotta do this. Well, there it is, right? How far is that from 0, 0? Just count down. 1, 2, 3, 4, 5, 6. That's it. I don't have to do anything fancy. It's not slanted. I don't even need the distance formula to do it. Of course it works, but I don't need it because it's all on the vertical axis, right? So we could have taken a shortcut and just said, yeah, I know that's 6 away because it's 6 down the y-axis. Okay? You can always use the formula. That's fine. All right, so that's how we find these distances. Now, which one is further from the origin? Which has a bigger absolute value of those two complex numbers? 6, yeah. Because 6 squared is 36, right? So 6 is the square root of 36. And the square root of 36 is obviously bigger than the square root of 29, right? So closest to the origin would be this one, smaller. Okay, and then here's where we kind of left off, adding and subtracting. Very simple. This is the nitty-gritty of what most of the assignment's going to be. You're just going to be doing arithmetic with complex numbers. Later on, we'll do some more stuff with it, but for now, this is pretty much it. Adding and subtracting, super easy. All you do, the trick is treat I like a variable. Just add up the like terms. So here I'd have -1 plus 3 is 2. 2i plus 3i is 5i, done. That's it. Okay? What if I'm subtracting? If I'm subtracting, just as easy. All I got to do is distribute the negative sign. So I've got 2, whoops. What's going on here? 2 minus 3i. And if I distribute the negative sign, I'm going to get a -3 plus 7i, right? If I add up like terms, I've just got 2 minus 3 is what? -1. And then -3i plus 7i. There it is. That's my answer. Couldn't be easier. And we can add up more than that if we want to. We can add up a whole bunch of numbers. Same deal. Just add up like terms. Okay? Now, what if we're multiplying? Okay, multiplying is maybe a slight step harder, but not much. Not much at all. Treat the i's like variables, and then when we're done, any power of I will just deal with using those patterns that we talked about yesterday. And almost the only one we ever use is I squared. What is I squared equal to? -1. Good. So that's the one we'll end up using. So if I distribute the negative I here, don't I just get -3i minus I squared? right? Whenever I see an I squared, automatically I turn it into a -1, and that's it. That's our answer. So negative 3i plus 1, but we want to write it in standard form. Remember that we always want to write it in the form a plus bi, so the number goes first, right? So it'd look like 1 minus 3i, okay? What about this guy here? All I do is FOIL it out, like I normally would. 2 times -6 is -12, 2 times -2i is -4i, 3i times -6 is -18i, 3i times -2i, isn't that -6i squared, right? What does the I squared turn into? -1, and just add up like terms. -4i minus 18i is -22i. -6 times -1 is +6, and then I'll just combine the +6 with the -12, and that's my answer. Okay, very simple. Okay, now the one that's slightly harder but not that bad is dividing. Here's how I want you to think about dividing complex numbers. This makes it easy. First of all, here's the problem we're actually dealing right there. Okay, how do we do these? Here's how I want you to think about this. Remember what we did with when we were dividing radicals. We had a rule. We said no radicals in the denominator, and so we had to get rid of radicals in the denominator if they showed up, right? And we did an example like maybe this. How about if we did square root of 5/8? How did we deal with that? Okay, we split it into square root of 5 divided by square root of 8, and then we simplify if we can. Can we simplify square root of 5? No, we're stuck with that, aren't we? What about square root of 8? Square root of 4 times square root of 2, so 2 radical 2. And then remember what our strategy was. If we have a radical that's stranded in the bottom, we have to just multiply the top and bottom by that radical. That's how we get rid of it. So in this case, we've got a square root of 2 stranded in the bottom. So we just multiply top and bottom by square root of 2. Okay, what's that give us on the top? Yeah, square root of 10. Good. On the bottom, now look at this. I've got square root of 2 times square root of 2. What's that? 2, right? When you multiply a radical by itself, it just undoes the radical because I'm squaring it. So I get 2 times 2 is 4, and that's my answer, right? So we had a strategy. If we had a radical stuck on the bottom, our strategy was multiply top and bottom by that radical. Well, the same thing is true, or a similar thing is true, for complex numbers. Same kind of a rule anyway. If we have an I on the bottom of our fraction, we have to get rid of that. We don't want I's in the bottom. So our strategy is we're going to multiply top and bottom, not by the complex number itself, but by its conjugate. Now, what does that mean? Here's the definition of conjugate. It's very simple. It's just a pattern. The conjugate of A plus B is A minus B. Okay? The conjugate of A minus B is, what do you think? A plus B. All you do, if I'm adding or subtracting two terms, the conjugate is just going to be the other one. If they're being added, I'm going to subtract them. If they're being subtracted, I'll add them. Okay? So then, for doing a problem like this, we're just going to multiply top and bottom by the conjugate of the bottom, which we call the complex conjugate because it's a complex number. That's the only reason it's a complex conjugate. It's got an I in it. So what if we do that? If I multiply the top and bottom by the conjugate of the bottom, see what happens. Okay. Well, that's what we get, right? Should include the parentheses. Now, if I just FOIL these out, watch what happens. Something important is going to happen, and the same thing happens every time. On the bottom of the fraction, when I FOIL this out, -1 times -1 is 1. Multiply the outside terms. -1 times positive 2i is -2i. Inside terms, -2i times -1, excuse me, is positive 2i. Look at that. Those terms cancel. The i's go away. It'll work that way every time. So that's good, right? Our goal, remember, is to get rid of the i's. So those go away, and then the last times last, I get negative 2i times positive 2i is negative 4i squared. And what's I squared equal to? Negative 1, right? And so I end up with no i's in the denominator, which was my goal. Now in the top, in the numerator, I'm going to get some i's. When I FOIL these out, I'm going to get some I terms and an I squared term, and that I squared goes to negative 1. But when I add all that stuff up, yeah, I'm going to get some i's in the top. That's all right. We just can't have them in the bottom. Okay, and so I get on the bottom 1 minus 4 times negative 1, just 1 plus 4, which is 5. And on the top, when I combine all the like terms, I just get that, negative 25 minus 5i, right? And then all I've got to do, remember, if I want to write this in standard form, I'm just going to write it as a number plus a number times I. I can split that into two separate fractions. Negative 5/25, or negative 25/5, sorry, minus 5/5 I. And in this case, those fractions reduce, but they wouldn't have to. They could end up splitting fractions. Negative 25 over 5 just becomes negative 5, and the 5's canceled here, and I just get negative 5 minus I. But those could have been fractions. That's fine. Fractions are numbers. And that's our answer. Okay? All right. So that's what you're going to be doing on the assignment. Not really a big deal.